नमस्कार बच्चों, मेरा नाम धन्या और हम ग्रेड 11 केमिस्ट्री का थर्ड लेसन सीख रहे हैं जिसका नाम है पीरियोडिक क्लासिफिकेशन ऑफ एलिमेंट्स. And in this video, we are going to study the periodic properties. Okay, now periodic properties are the properties that repeat itself after certain intervals of time or that show gradation of the properties. Maybe it increases or decreases. So that is called as periodic properties. Okay, so there are several properties we have to study. First of all, the first property that we are going to study is the atomic radius. Okay, so how atomic radius varies, changes across the period or along a group. Okay, now atomic radius, what is atomic radius? Okay, suppose we have a nucleus and we have the electrons moving around the nucleus. So initially, or you would have studied the definition before as the distance of the valence electron or the last electron from the nuclei. That is called the atomic radius. Right. But later it was found out that electron is not a particle, it has wave nature. So electron behaves as a wave. So do you think this definition will be suitable for it? So if electron is behaving as a wave, so that means the boundaries of the electrons are not defined. So if it is behaving as a wave, it will be something like this, right? So you don't have clear-cut boundaries, right? So boundaries are not defined. So radius is not measured this way. It is measured in a different way. Instead of free state, we measure the radius in bonded state or in interaction state. Why do we have to measure like this? Because the electron behaves as a wave, it doesn't have clear-cut boundaries. So we measure the radius not as free state, but in the bonded state or in the interaction state. Okay, bonded. Atoms are bonded. Okay, so in the bonded state or the interaction state, the type of atomic radius that we have to study are, so in the bonded state or in the interaction state, what are the type of atomic radius that we have to study? First one is covalent radius. Okay. Next one is van der Waals radius. Next one is metallic radius. And the last one is ionic radius. Okay. So in the bonded state, we have to study these four kinds of radius, atomic radius. So the first type of atomic radius that we are going to study is, the first one is covalent radius. Okay. Now students, you must be knowing that covalent bond is formed between two same or different nonmetals. But for now, first one, we would be taking the case of two same nonmetals, okay, by the sharing of electrons. So this is atom A. I'll make it a bit bigger. So I'm taking two same nonmetal A and A. Okay, by the sharing of electrons. So in covalent bond, sharing of electron takes place. Okay, so this is covalent bond, but covalent radius is 1/2 of the distance between the nucleus of the two covalently bonded atoms of the same element. So this is the nucleus of first atom A. This is the nucleus of the second atom A. So this is the 1/2 of the distance between the nuclei of two covalently bonded atoms. Okay, so this distance is DAA. Okay, so what is covalent radii? Covalent radius is 1/2 of the distance between the nuclei of two covalently bonded atoms of the same element. I have taken the same element A and A in a molecule. Okay, and this distance is also called as bond length. So we can also write it this way, 1/2 of the bond length. Okay, so this is the covalent radii for a molecule in which both the atoms are of the same element. Both the atoms are of the same element. Now, in case this is same atoms, same element. Okay. Now, in case if the atoms are not same. Okay, but the electronegativity is same. Electronegativity we will be learning later, but in short, electronegativity is the capacity to attract electrons towards itself. Okay, suppose I have atom A and atom B. This is atom A and B, different element, they form covalent bond. Okay, now the electronegativity, suppose it's same. For example, methane, CH4. Both carbon and hydrogen have similar electronegativities. Okay, the atoms cannot pull the electron cloud towards itself fully. Okay, so in this case, the covalent radii is given by DAB equal to RA plus RB. Okay, so radius of A plus radius of B. Okay, but this is a case when the elements have same or similar electronegativity. And please remember, this is formed between molecules of non-metals, okay, where sharing of electrons is taking place. Okay, so the distance AB is given by radius of A plus radius of B. Okay, now this is covalent radii. This is the first case. This is the second case. Now I have the third case where if the electronegativity is different. So I have different electronegativity. Just to drop this part and make some space for C, where they have very different electronegativity. That means electronegativity. That means one atom can pull the electron cloud towards itself. Okay, like HCl, like hydrogen chloride. Chlorine is more electronegative, so it can pull the electron cloud of hydrogen towards itself. In that case, there's a small formula. So suppose A and B. This is A, this is B. So in this case, the atomic radius is given by RA, radius of A, plus RB, radius of B, minus, we are subtracting the electronegativity. Okay, we are subtracting the electronegativity effect. Okay, so xi of A minus xi of B. Okay, so this is the case if electronegativity, this electronegativity of A is more than B. If it's other way around, just do the other way around. Okay, so xi A and xi B are the negativities of A and B respectively. Okay, so in case of hydrogen chloride, we can use this formula if the electronegativity of A and B is known. Okay, so students, this is the covalent radii. Covalent radii, if the covalent bond is formed between atoms of elements of same elements, okay, if the sharing of electron takes place between same elements, it is half of the distance between the nuclei of two covalently bonded atoms, okay, of the same element in a molecule. In case if the atoms are not made up of case B, where the atoms are not the same or the elements are not the same, then we have two cases in that. In the first case, where the elements have similar electronegativity, then it is just we just have to add the radius of A and radius of B. Okay, and where RA and RB are the radius of A and B. And in the third case, where there is electronegativity difference, like the case of hydrogen chloride, then there's a small formula which you need to memorize. Okay, here we just have to subtract the electronegativities. Okay, so this is atomic radii. Okay, students. Now we move on to the next case. The next type of radius is the van der Waals radius. Okay. Now, van der Waals radius is formed for molecules or atoms that do not form any bond. Okay. For example, in case of two molecules, okay, hydrogen and hydrogen molecule, okay, there is no bond formed, but they do attract each other. Okay. And that is why if they come closer, there is intermolecular forces of attraction. Okay, so there are several hydrogen molecules or several oxygen molecules, or in case of noble gases, okay, the atoms are near each other. They have some small forces of attraction. Okay, now these attraction between the molecules is called as intermolecular forces of attraction. That keeps the molecules together. Okay, now in case we have to find the radius for these kinds of molecules, we have to take the closest approach. For example, if I take one molecule AB, okay, there is another molecule, suppose AB, okay. Suppose in this molecule, there are many molecules of A and B, AB, okay. Now, suppose I have to take the I need to measure the distance, or I need to measure the van der Waals radius. Okay, because there is no bonds formed, it will be van der Waals radius. Okay, so van der Waals radius of suppose B. It will be the closest approach, distance of closest approach, that is represented by dBB, where dBB is the distance of closest approach. When they are very close, how much is the distance? Closest approach. Okay, divided by 2. Similarly, if I have to find the van der Waals radius of A, so van der Waals radius of, van der Waals radius of A, I will take the closest approach of A. So that is AA, DAA by 2. Okay, so in van der Waals radius, it is just the closest approach, distance of closest approach by 2 divided by 2. Now, this is for molecules. We also use it for noble gases, because in noble gases also, it's just the forces of attraction. There's no bond form. So in case of, I have 2 helium atom, there are many helium atom, okay? And here, if I'm taking the 2 helium atoms, okay, there is attraction between them, light attraction between them. So suppose this is there is no bond formed, and this is the closest approach of helium atom, okay? So we measure the distance of closest approach by 2. Now here, in this, so we learned about the covalent radius and we learned about the van der Waals radius. Now here, a comparison can come. These questions are very important, okay? A comparison can come. Which radius is bigger? Van der Waals radius or covalent radius? Van der Waals radius or covalent radius? Now, in van der Waals radius, we are just measuring the closest approach, because the molecules also have some, there is no overlap. Molecules also, if they cannot come very close, if they come very close, then there will be repulsion between the electrons, right? So they cannot come very close. Neither there is any overlapping or anything going on. But in covalent, there is overlapping of the atoms. That makes it smaller, right? So which one do you think will be bigger? Definitely, no doubt, the covalent radius, the van der Waals radius is bigger than the covalent radius. For the reason that in van der Waals radius, there is only distance of closest approach. There is no overlapping. They can come only to a certain extent. They can come closer to a certain extent. There is no overlapping going on. Okay. So if after a certain limit, the valence electrons start to repel each other. So that's why there is a limit. So that's why van der Waals radius is greater than the covalent radius. Okay. Okay, students, the next atomic radius that we are going to learn is metallic radius. Okay, now in case of metals, metal alone, if I take an iron rod, or if I take copper, any metal alone, they themselves cannot form a covalent bond or ionic bond, okay, but they form a special type of bond which is called as metallic bond. Okay, so in metallic bond, what happens is that there is a lattice of metal ion, there's a lattice of metal ion, and they are arranged in a certain array, and there is a sea of free electrons that is moving around freely. Okay, it's a sea of free electrons moving around freely, and the metallic radius basically is one half of the distance between the nucleus of the 2 metal atom in the lattice. So there are the 2 metal atom, half of the distance between the nuclei of 2 metal atoms. Okay, and this is called as a metallic radius. Okay, so you don't have to study metallic radius, you don't have to study metallic bond, but you have to know what is a metallic radius, and this is the formula. So it is half of the distance between the nuclei of 2 metal atom. Okay. Now, if we have to compare, so this is the metallic radius. Now suppose we have to compare between van der Waals radius and metallic radius and ionic radius, and covalent radius. Okay, if I have to arrange them in the order, which one is bigger and which one is smaller? You know, always the van der Waals radius will be more because there is no overlapping. Okay, and the atoms can, or the molecules can come only till a certain distance, come near to each other only till a certain distance. After that, the electron starts to repel each other. So that's why van der Waals radius is greater than metallic radius. Okay, and metallic radius is greater than covalent radius, because in covalent radius, you know, there is overlapping that reduces the size. Okay, so this is the order which you must remember. Okay, so this was the three types of radius till now we discussed: covalent, van der Waals, and metallic radius. Now we will learn a bit about variation along the period and group, and then we will come to, we will discuss some exceptions, and then we will come to ionic radius. Okay, now coming to variation of atomic radius along a period, which is very important. Along a period and group, the variation is very important. A lot of questions are asked from this part. Okay, so variation of atomic radius along a period and along a group. Down the group. Okay, now first we will discuss along the period. Okay, now students, if I take any period, okay, so first we will learn along the period from left to right, how the atomic radius is varying. Okay, now lithium, let's take the second period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and then neon. Okay, now we have Z is the number of protons. Z is 3 for lithium, 4, 5. It keeps on increasing, right? It's elements are arranged in increasing order of their atomic number. So the configuration is 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2, 7, and 2, 8. Now, as you move from left to right, what is happening to Z? What is happening to the number of protons? Number of protons increases. P stands for proton, okay? P stands for protons. So number of protons increases. We call it as nuclear charge, okay? So nuclear charge increases. From where to where? From left to right. So number of proton increases, that means nuclear charge is increasing from left to right. So that means if in case we have, in case of Lithium. We have 3 protons. 3 protons and 1 electron. So that means it will attract the electron. The proton's positive nucleus will attract the electron. Okay, as we move towards the right, maybe I'm coming across carbon. Carbon, there are 6 protons. That is attracting the 4 electrons. So number of charge is increasing, right? So the nuclear charge is increasing. So that means the pull of the electrons towards the nucleus will also increase because the charge of the proton or the positive charge is increasing in the nucleus. Now, coming towards the fluorine, okay? Coming towards fluorine, it is 9p. So as you're moving from left to right, the nuclear charge is increasing. As the nuclear charge is increasing, the nucleus will pull the outer electrons towards each other more. So what will happen to the radius? Radius size decreases, so that means radius decreases. So along the period, radius decreases. Okay, exceptional case I'll be discussing. So I'll just finish with the group also, and then I'll discuss the exceptional case also. Okay, or rather here itself I'll just discuss it. So as you move from left to right, what happens to the radius? Radius decreases because what's happening to the nuclear charge? Nuclear charge is increasing. So the pull of the electrons towards the nucleus is more. Okay, I hope till here it is clear. Okay, now here, I'll discuss the exception here itself. Okay, now we have lithium, so that means lithium is greater in size than beryllium and so on, right? Oxygen is greater than, so as you come towards the right, the radius is decreasing. Okay, but it is found that neon is having a greater radius than whom? Lithium. Okay, this is because of, we already discussed this, neon is a noble gas. Okay, and noble gases have what kind of radius? Van der Waals radius. And Van der Waals radius, neon has what kind of radius? Van der Waals radius. Because they don't form bond. Okay, so if neon has Van der Waals radius, it will be greater in size than the other type of bonds that's formed between other elements, right? So it is greater, Van der Waals radius is greater than covalent radius or even metallic radius. Here there's no metal, sorry. Here there is metal, but it is, so Van der Waals radius is greater than the covalent radius. Yes, similarly, there is another exception for hydrogen and helium. Okay, period 1. This is period 1. Okay, so as you move from left to right, what would happen? It should decrease, but helium is found to be having a higher size than hydrogen because of the same reason, Van der Waals radius. Helium is a noble gas. Noble gases have Van der Waals radius. which is greater in size than covalent radius. Okay. Now, coming to down the group. I hope this is clear. Now down the group. Now down the group, I'm sure you will be able to guess. Down the group. Now down the group, as you're moving down the group, what is happening to the number of shells? For example, lithium. It is 2,1. Sodium, 281. Potassium, 2,881, etc. So as you're coming down, what is happening to the number of shells? Number of shells are increasing. What happens to the valence electron, the outer electron? Does it is the valence electron becoming far from the nucleus? Yes. So what happens to the valence electron is far from nucleus as you're coming down. So what happens to the size? Size increases down the group, or atomic radius increases down the group. Okay, so here if I make a rough chart like this, so along the period, the atomic radius decreases. If along the period it is decreasing, definitely it will increase along a group. Okay, so this was the trend. Okay, now coming to another exception for in case of the D block element. So in case of D block elements, if I take an example of maybe scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, and zinc. Okay, so 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. Okay. Now, this is a period, and in reality, what should happen? The radius must decrease along the period from left to right because the nuclear charge is increasing. Nuclear charge increases, so the size must decrease. Now, it has been found that for scandium, titanium, and vanadium, the radius decreases. As you move from left to right, it is decreasing. And for the next 4 of them, it remains the constant. Constant means it remains almost same. And the last 3 of them, it increases. So isn't it showing a different behavior, okay, compared to the other elements in the periodic table? Okay, so this is for D block elements. Okay, now here this is the 3D series. Okay, so this we are talking about the D block elements. So this is the 3D series. Now in scandium, I'm just writing the D configuration. Here the number of electrons will be D1. Here in titanium, it will be D2, D3, For chromium, it is an exceptional case, half filled. So this is D5. Manganese is D5. This is D6, D7, D8. And copper is an exceptional case, D10, and zinc also D10. Okay. Now, if you see the first three cases, the first three elements, okay? Here, the nuclear charge is increasing. Yes, the nuclear charge increases. Nuclear charge increases, yes. Here, as the nuclear charge is increasing, the electrons or the outer electrons are pulled by the nucleus. So, what is happening to the radius? Atomic radius is decreasing. Okay. But if you come to the next set of elements, here what is happening? The nuclear charge Z increases. Yes. Here the nuclear charge is increasing. Yes. But at the same time, number of electrons also increases. That means, for example, if I say 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. Next, it starts to pair up, right? So when it starts to pair up, what is happening to, there will be a slight repulsion between all electrons also. So this nuclear charge increase and electron-electron repulsion balances each other. So what is happening to the atomic radius? There's not much increase. It remains constant rather. Because the proportion in which the nuclear charge is increasing, the electron-electron repulsion is also seen. So both of them balance each other. And so there is not much increase or decrease. Nothing is seen. It's almost constant. Okay. In the next set of elements, the nuclear charge increases, yes, but the number of electron also increases in large numbers. So as the number of electron increases, what's happening to the electron-electron repulsion? Also increases a lot. So who dominates? The electron-electron repulsion dominates. So what happens to the size? Size increases. Okay, so this is the reason for a different behavior for this series or the D block elements. Okay, so that is why they are behaving in a different way. Okay, so the first three elements, it shows the normal behavior. That is, as you go from left to right, it is the atomic size is decreasing. Okay, next set, it remains constant because as the nuclear charge increases, there's also increase in electron-electron repulsion because the number of electrons are increasing too. Okay, but here they are balancing out each other, so there is not much change seen. But in the next set, as the nuclear charge increases, the number of electrons also increases more. So the electron-electron repulsion dominates over the increase in effect of increase in nuclear charge. So what is happening to the size? Size increases. Okay. So this is one of the exceptional behavior. Okay. Now, again, more about the D block element. Again. Okay. I have taken 3D series, 4D series, and 5D series. Okay. Scandium, yttrium, lanthanum, titanium, zirconium, and HF, vanadium, NB and DA. Now this is 21, different color. This is 21, 22, 23. This is 57. This is 72 and 73. Okay. Now, this is the 3D series, this is the 4D series, and this is the 5D series. Okay. So, 4D, 3D series. Okay. Now, student, you know this range from 58 to 72 is the lanthanides. Okay. Down the group, we learned that the radius increases because the valence electron is moving away from the nucleus. Right. But it is seen that for this group, scandium, okay, for the first 3D series, scandium is lesser in size than yttrium, is lesser than lanthanum. Okay. But in the next two cases, it is seen that titanium is less than zirconium. That's fine. But zirconium is equal in size than HF. Zirconium is similar in size to hafnium. Okay. And similarly, in the next one, vanadium is less than Nb, niobium. Vanadium is lesser in size than niobium, which is similar to Ta, thallium. Okay. Now, why this happens? Okay. That means 4D elements, 4D series elements having a similar size than the 5D elements, 5D series elements. Why this is seen? Okay. Now, we know that from 58 to 72, atomic number 58 to 72, we have the lanthanides. Okay. Now, here, lanthanides means 4F subshells come into play. Lanthanide is from 58 to 71. Okay. Okay. Now, students, 58 to 71, we have the lanthanides. So, the 4F subshells come into play. So, that means when it reaches atomic number 71, even if there is, or the atomic number 72, even if there is an increase in the number of shells, it shows a decrease in the size. Okay. This is because of something called lanthanide contraction, which is very important. Okay. Now, what is this lanthanide contraction? Now, students, in a multi-electron system, you know the electron, then positive nucleus attracts the electrons. Okay. Now, in a multi-electron or multi-electron system, the nucleus attracts the electron, yes, but the inner electrons shields the outer electron. The inner electron shields the outer electron from the nucleus. It's like a shield. Okay. So, when it shields, that means if there is shielding, that means this electron will not get the positive effect of the nucleus, right? If the shielding is more, if the shielding effect, if suppose here in this case, this electron is shielding this outer electrons. So that means this outer electrons will not get the attractive power of the nucleus or attractions of the nucleus, right? So because of which the size will not reduce, right? Now, Now, students, in case of the orbitals, the most shielding effect is from s orbitals. Okay, this is the order of shielding effect I'm writing. Order of shielding effect. Acting like a shield. Okay, now here S has the maximum shielding effect. It shields the outer electrons. Next is P, next is D, next is F. Okay, S has maximum shielding effect because of the shape. And F has the poorest shielding effect because of that eightfold shape. F has the poorest shielding effect. Now, what happens if the shielding effect is poor? That means if suppose the F electron is not able to shield the outer electrons. So this outer electrons will be attracted towards the nucleus. So what happens to the size? Size is reduced. So size reduced. So because of the lanthanide contraction, this lanthanide contraction or screening effect, you can say, and because of why the screening effect or lanthanide contraction happens, because of the poor shielding effect of f orbitals. Because of this, 4D and 5D have similar size. Okay, so this is the trend that is followed for the 4D and 5D series. Okay, so quickly, students, okay, students, 4D and 5D have similar size. Okay, this is because of what? Lanthanide contraction. Why this lanthanide contraction happens? Because of the poor shielding effect of the F orbitals. Okay, so which is why the outer electrons are attracted towards the nucleus more. So what's happening to the size? The size will reduce. So this is an important part of the lesson. Okay, so students, coming to ionic radius. Coming to ionic radius. Okay, students, you know the ions. Ions are charged particles, right? Now, in case of any element, if it is losing an electron, it forms positive ion. If it is losing an electron, right? So this is cation. And if any element is gaining an electron, it will form anion, right? Comparing the size of cation and anion, always anion has a greater size than atom, neutral atom. It has a greater size than cation. So cation is the smallest and comparatively anion is bigger. Okay, why this happens? If suppose we talk about cation, okay, I have a positive nucleus, and suppose initially there were 2 electrons. Okay, and suppose in case 1 electron is removed, suppose just 1 electron is removed. So the effect of the nucleus on the electrons will be more. Okay, so the nucleus will attract the rest of the electron more, or nuclear charge increases. So what is happening to the size? Size is decreasing. Okay, so the opposite thing happens for anion. For anion, what's happening? Suppose before there's a positive nucleus. Suppose before there was 1 electron, and suppose 1 electron got added up. So what's happening to the nuclear charge, or what's happening to the effect of nucleus on the outer electrons? It's becoming less. Okay, so what's happening to the size? Size is increasing for anions. And also here, one more thing that affects is the electron-electron repulsion, where it will be slight. Okay, so what's happening to the size of anion? It increases compared to cation or the neutral atom. Okay, so this order you have to remember, that anion, it is bigger compared to neutral atom, which is bigger compared to the cation. Okay, now sometimes they ask you to arrange the anions in increasing order. Okay, for example, if I have H plus and H minus. So just follow this order, where anion is bigger in size than neutral atom, which is bigger in size than cation. Okay, similarly, I have O2 minus, O minus 1. More the negative charge, bigger is the ion. Okay. Now here, because this in O2 minus, that means 2 electrons are added. In this O minus 1, only 1 electron is added. So definitely O2 minus will be bigger in size than O minus. Okay, so this is how you do it. Okay, so just write as an important note, more the negative charge, more is the, or greater is the size. This is an example that we have done. Okay, similarly, if I take an example of chromium 3 plus and chromium 6 plus. In grade 12, you have a lesson on different oxidation states of these transition metals. Okay, so you will be learning that some transition metal, they have more than one oxidation state. So this is one of them. So you will be learning that in grade 12. For now, if I have given you 2 ions, chromium 3 plus and chromium 6 plus, who is bigger and who is smaller? Okay. So in case of negative, if there is more negative charge, that means more is the size. Here, in this case, in chromium 3 plus, it has lost 3 electrons. In this case, it has lost 6 electrons. So that means who will be bigger in size, and who will be smaller in size? This has lost only 3 electrons. So greater than chromium 6 plus. Here, students, in chromium 6 plus, this particular chromium has lost 6 electrons. If it has lost 6 electrons, that means the attraction of the positive nucleus on the rest of the electron is more. So definitely the size will be less. In the other case, chromium 3 plus, it has lost only 3 electrons. Okay, so comparatively, who will be smaller? Chromium 6 plus will be smaller than chromium 3 plus. So just write down as a small note, more positive ion has smaller size. Just the opposite of that negative sign. Okay, similarly, if I take an example of manganese 2 plus, manganese 4 plus, manganese 6 plus. Okay, so this is also transition metal having variable valencies. So here it has lost 2 electrons, 4 electrons, and 6 electrons. So definitely whoever has lost less number of electron will have a higher size than the rest of it. Okay, so this is how you do. Okay. So along the period, so let's go to the trend of ionic radius along the period and along the group. Along the period, what's happening from left to right? What's happening to the charge? Charge is increasing. So it's a regular trend. When charge is increasing, what's happening to the radius? Radius will decrease because it will pull the outer electrons towards the itself. The nucleus will pull the outer electrons towards the nucleus. So it's a regular trend. If along the period, if it is decreasing, what happens down the group? It will be the opposite. It will be radius will increase, is just the opposite. Radius increases. Okay, so this was for ionic radius. Okay, so more questions about this we will be doing when we do the past paper questions after I complete the lesson. Okay, so just keep in mind the trend of all the different kind of radius and also the exceptions that I just completed for the D block element. Okay, now coming to something called isoelectronic species. Okay, isoelectronic species. So isoelectronic species. What is this isoelectronic species? That means the species that have same number of electrons. For example, if I say O2 minus, okay, N3 minus, F minus, Na plus, Mg2 plus. Okay, here this oxygen ion has 10 electron, nitrogen has 10 electron, fluorine has 10 electron, sodium has 10 electron, magnesium has 10 electron. So all of them have the same number of electron. They are considered to be isoelectronic species. Please remember the term because sometimes they use in the questions. Okay, isoelectronic. So they just mention this is isoelectronic. So you must keep in mind that those species that have same number of electrons. Okay, now for isoelectronic species, you don't have to look at the group number or period number or anything like that. You have to just remember the size is inversely proportional to atomic number Z, where Z is what? Z is the atomic number. Okay, so if you come across isoelectronic species and they ask you to arrange the elements according to their size, you just have to remember the atomic numbers. If it's given, well and good. Okay, so in this case, The atomic number I'll just mention in blue. Okay. For Z, for oxygen, it is 8. For nitrogen, it is 7. For fluorine, it is 9. For sodium, it is 11. Magnesium, it is 12. So this is the atomic number for these elements. Okay. Okay. Now, if we have to arrange these elements in increasing order, or if we have to arrange the elements according to their sizes, what do we do? So the size is inversely proportional to atomic number. So whichever ion has or whichever element has greatest atomic number will have smaller size. So who has the greatest atomic number among these is magnesium, right? So magnesium ion will be smaller in size, smallest in size comparatively for this series. Okay. Then next one is what? Next one will be sodium. That is the next higher atomic number. Next one will be fluorine. That is the next higher atomic number. Next one will be nitrogen. Nitrogen or oxygen? Oxygen. Because oxygen is 8. Atomic number is 8. Next, the last one will be nitrogen, which is the bigger in size. Okay, so size is inversely proportional to the atomic number. Okay, so you don't have to check the group number. You don't have to check the period number, etc. Okay. Now, similarly, another example if I give. Suppose if I take sulfur 2 minus, phosphorus 3 minus, and chlorine minus. Okay, and the atomic number for them is 16. This is 15. This is 17. So let's check is it isoelectronic? So 16, atomic number is 16. It is 2 minus. So that means it has gained 2 electrons. So that means number of electrons now is 18, because 2 minus means electron has come. 2 electrons have come, has been received by sulfur atom. Okay, here 15. It's 3 minus. So 3 electrons have come. So 18 electron. This one, chlorine. The atomic number is 17, but it is 1 minus. So that means 1 electron has come. So 18 electrons. So it's isoelectronic. So for isoelectronic, what do we check? We don't check the group number or period number. We check the atomic number, right? So atomic number, which one is, the atomic number of which element is more? For chlorine is more. So that will have the smallest size. Then the next element is sulfur. Then the next element is phosphorus. Okay, so this is how you arrange the elements for isoelectronic species with same number of electrons. Okay, so students, in the next video, we will be discussing some more periodic properties and periodic trends. Okay, so that's all for today. Have a great day, students.